Okay. So the last big theorem was the fundamental theorem of linear algebra. So what was that? So the null space is also known as the Rn. So if n is A is n by n matrix, then the Rn can be decomposed into two subspaces, the null space and the row space. And these two guys, they form a direct sum end of the entire vector space Rn. And they are on top of that, they are orthogonal to each other. And the same is true for the left null space and the column space. So these guys are mutually orthogonal complement to each other. So why are they so important? So they are important. So especially if you try to find the behavior of the matrix A as a linear transformation. I told you the matrix can be always considered as a linear combination between two spaces. And in particular, so if my A is n by n matrix, and in that case, the A can be considered as a linear transformation from Rn to Rm. So an n by m matrix as a linear transformation from Rn to Rm. And this Rn, this one can be written as a direct sum of the null space and row space. And this Rm can be written as the direct sum of the left null space and the column space. So I told you that A can be considered as a linear transformation from Rn to Rm. And this is an n by n matrix. Then A is a map from Rn to Rm such that A is being mapped to A times X. So this is an n-dimensional column vector. And if you multiply A by this column vector, then the resulting matrix is a n by 1 column vector. So this one also can be considered as a member in Rn. Now, also, why is it something to do with these two decompositions? So here, I say this guy was decomposed into the null space and the row space, and this one has been decomposed into the left null space and the column space. And this decomposition is very important. So if you try to understand the behavior of this map A, so like this, just choose any vector from your domain. Then, since we have such a decomposition, so this vector can be uniquely written as a linear combination of the vectors from the row space plus the vector from the null space. So XR is a member of the row space. Member of the row space, and Xn is the member of the null space. Then AX is, now I want to find the image of this vector under this linear transformation. So this is the image, but x can be replaced by xr plus xn. But since xn is the member from the null space, so which is the same as xr, I want to consider my matrix A as a collection of the columns and columns. Well, obviously, this is XR. And the result is just a linear combination of these columns. And therefore, the resulting vector must be the member of the column space of A. So if you try to understand A as a linear transformation from Rn to Rm, then the image of every vector from your domain is always lies in the column space of A. So if I want to borrow the rank terminology from the set theory, so I can try to say the range of these vectors, the range of this linear transformation is the column space. Okay. And on top of that, I can even say this. Let me focus on the dimensions of these spaces. This guy, the row space and the column space, those two spaces have the same dimensions. Those two guys have the rank dimension of these two spaces are the rank R. And since NA and NAT, they are complementary dimensional spaces. So dimension of this guy is just a rank n minus rank R, and this is m minus rank R. I just okay. So I just want to say that these two guys have the same dimensional spaces, and I feel like those spaces are somehow related to each other under the linear transformation A. And that is actually true. Every matrix, A transforms the row space bijectively onto its column space. So, so that means, well, this matrix A as a map from Rn to Rm, it may not be necessarily injective or surjective. But if you just focus on this domain, this guy, so if you just restrict the domain, so if you consider this guy not a function from Rn, but if you consider this guy as a function from the row space of this row space of A, then in that case, this one is mapping this guy bijectively onto the column space. You know, those two spaces have the same dimensions. And so the restriction of domain onto the, restriction of domain to the row space makes this linear transformation as a bijective map. Bijection from CAT to CA. Do you know what I mean by the bijective map? So have you ever heard about the bijection? So, well, bijection, I mean by this. So in set theory, if you have a function between two spaces, then and we say the function is bijection. So if there is the function is bijection, if it satisfies these two conditions. First, there has to be a one-to-one map from the domain to codomain. It's a one-to-one. One-to-one, I mean by if any two guys from your domain is map has the same image, then those two guys must be the same. Those two guys in the domain must be the same guy. So there can be no two different guys from your domain that has the same image. So that is what I mean by the one-to-one. And the second condition is the function has to be surjective. So what do you mean by surjection? So the function is surjection if every member from your domain, every member of your domain must be the image of some other guy from your domain. Oh, sorry, I messed up. I will repeat. So the function is surjection if every member from your codomain is an image of some member in your domain. So that is what I mean by surjection. So if your map is bijection, then that means the map function has to be one-to-one and surjection. So that means there is like precisely one-to-one correspondence between the domain or every element from your domain and every element from your codomain. So that is what I mean by surjection, so bijection. So if you can build any bijection from between any two sets, then that means those two sets have roughly speaking, those two sets, they have the exactly same number of elements. All right. So to prove this, so here I'm gonna say the linear transformation A restricted to the low space is a surjection and the bijection. I will try to prove the surjective first. In order to show that the function is surjection, then I will need to choose any guy from its column space, and I should be able to see that this guy is the image of some other guy from the row space. Okay, how can I show this? Since B is a member from the column space, therefore the system of this equation must have at least one solution, right? Let me say X. Now, X is this is an X is a member of n-dimensional space. So X is from the domain, and domain can be written as a direct sum of the null space and the row space. So X can be written as a linear combination of the vector from the row space and the vector from the null space, right? And such a linear combination is unique. Now, AX was the solution of the equation, solution of the system. So this is B, but at the same time, this is AR. So here, so A times XR, so XR, yeah. I need to emphasize that this is from the row space. And that means I could find a vector from the row space such that under the linear transformation A, this guy is being mapped to the vector B. So this may be surjection. Now, injectivity or one-to-one. Injection, one-to-one and injection, they are the same thing in the world of mathematics. Suppose that I could find two vectors from the row space whose images are the same, such that AXR is AYR. So these vectors are clearly the member of the column space. And if you take the subtraction, then this is the zero vector. So this vector multiplied to the vector matrix A was 0. That means this vector was a member of the null space. Now what? Yeah, okay. So XR and YR, they were chosen as a vector from the column space, row space. So XR minus YR is a member of the row space too. And it says this is also a member of the left null space. And there's precisely one vector that lies in the intersection of the left null space and the row space. What was that? The zero vector. So XR minus YR must be the zero vector. So those two, it turns out these two guys are the same vectors. So that means if these two vectors have the same image, then they must be the same. So this proves the injection. So this is an injection and surjection. Therefore, the function is the bijection. So this is a little schematic picture that explains the entire situation. I would say this is Rn, this is Rm, and matrix A is an m by n matrix. So considering matrix A as a linear transformation from Rn to Rm, then if this is the row space, if this is the column space of matrix A, then that means this entire vectors from your domain, it has been squeezed just to fit up this one single line, right? So this is the range of this linear transformation, this function. Okay, but however, since this this is one-dimensional vector space, therefore there has to be a one-dimensional row space from your domain, right? Why? Because if you believe in the theorem, the row space and the column space, there has to be bijection, so they must be isomorphic as a vector spaces. So dimension of this guy must be the same as the dimension of the row space. So I'm going to just draw some random one-dimensional vector space from the domain, and I will say this is my row space. And according to our theorem, there is a bijection between this from this to there. So this means A C A T. This is a mapping from the from mapping from the row space to the column space. So here I put this equilibrium sign here just to emphasize that this maybe is a bijection. By the way, have you ever seen this symbol before? This means the restriction of domain symbol. So what is the restriction of domain? Suppose that you have some arbitrary function, then the function is but you are always free to just restrict your domain. So if you take some random subset from your domain, and if you take this random subset as your domain of your function, then that means you have restricted the domain. And originally this guy has the time domain of this one, but if you just restrict the domain of this guy as this one single line, then there is a bijection from here to there. And what about all the other vectors? In particular, if you take the orthogonal complement of this one, then every vector in this space should be mapped to where? 0. Why is that? Because the orthogonal complement of this space has to be the null space. And by the definition of the null space, every vector that belongs to in this space should be mapped to the 0 vector right here. Okay, under this linear transformation. What about this vector? What about some random vector? Right. So you have to decompose the vector, and this vector can be decomposed into as a sum of this component and that component. And this component goes to somewhere over here, and this component should go to the 0. Okay. So this is how you understand the matrix A as a linear transformation. So once you understand the matrix and once you understand these two decompositions, these two orthogonal complement over here and over there. I should not forget that this is the left null space. So once you understand these two decompositions, then now you know which vector is being mapped to where, at least schematically. Okay. By the way, what happens if you take the transpose? If you take a transpose of your original matrix, then this is an n by n matrix. So that means now this guy is being linearly transformed into this space. So from this viewpoint, this is my new domain, and this is going to be my codomain, right? Although they look quite different, but I am pretty sure that this space is now being bijectively mapped into the low space under this transformation. Okay? All right. So similarly, the A transpose transforms the column space bijectively onto the row space. Okay, and I have prepared two silly quizzes. Quiz number 1. I want you to consider this map. So what is this? A has been followed by A transpose. So, and domain has been restricted to the row space. So this symbol implies that this guy under this linear transformation is now being biject mapped into this space. And after that, now because of this A under A transpose, now this one is now being mapped to the bijectively onto the row space, right? So this is a map from the row space to the row space. Now question is it always the same as the identity map? What do you think? Yes? No? The answer is no, not necessarily. That means this is not true. Well, yeah, this is clearly bijection. So, well, if you compose these two maps, then this is clearly mapped from this space to that space. And this is clearly, again, a bijection because you have composed two bijections. Therefore, the resulting map has to be bijection. But not every bijective map is the identity, right? So this guy cannot be identity. This guy may not be identity. Sorry, this guy may not be identity. Oh, I messed up. This is an example. So this is 2 by 3 matrix. And if I take a transpose of this and multiply it all together, then the resulting matrix must be this looking, this 3 by 3 matrix. And as you can see, so this is not the identity, even if you restrict it to the row space. So this is, well, so this claim is not true. The quiz number 2 is even more interesting. What do you think about this claim? I have some random matrix, n by n random matrix, and it has rank R. Now, I multiply it by the A transpose. Is the rank remains unchanged under this multiplication? Right, this is true. Yeah. Although in order to prove the statement, in order to give you the official proof of the statement, then, well, we'll need to wait just one more lecture. So, I mean, that means I'm going to give you the official proof in my next lecture. But I can still try to explain it like this. So, what is the rank? The rank means the dimension of the column space, right? So, if my rank is R, that means this guy has dimension of R, okay? But if you multiply by A transpose, then the dimension of this guy is the same as this one, but dimension now, this guy is now being mapped to this space under A transpose. So that means, well, the dimension of the column space of this guy, which is this, must be the same as dimension of this guy, right? Because these red lines, there is always bijection between them. So if this rank of this guy is R and the rank of that guy must be R. This is my intuitive, cartoon-based proof of this. Sorry about this, but I think I can give you the formal proof in next time. Yeah, sorry. All right. In this section, we will be talking about the projection. Actually, as a matter of fact, we have discussed the projection earlier. So when? So we discussed the two-dimensional projection, the projection in 2 dimensions, right? So projection in 2 dimensions was, well, we discussed the matrix representation of the projection in 2 dimensions. Which was actually a rank 1 matrix. And in this section, I want to generalize the result. We will be talking about the projection in higher dimensional vector spaces, not only in 2 dimensions, in higher dimensions. And also, speaking of projection, there are 2 types of projections. Well, one is the projection onto a 1-dimensional subspace. So which is this? I have two vectors, and I want to project this guy onto this subspace. Well, this is a clearly one-dimensional subspace, and then in order to get a projection, then I will need to take a foot from this endpoint to this point, and once this foot made a right angle, then length from here to there is going to be the projection of this guy onto this space. And since the dimension of this space is one-dimensional, and I say this is a one-dimensional projection. Okay, but however, you can think of some another projection. Like you can try to think of a projection onto two-dimensional subspace. So if this is a vector, and I want to project this guy onto this two-dimensional subspace, this is still okay, right? So the idea is the same. You just make a foot from this point to that point, so that it make a right angle, and this guy is going to be the projection of this guy onto this two-dimensional space. So there are many. So likewise, you can think of many projections. So projections onto not in one-dimensional plane, so not in one-dimensional space, but on higher dimensional subspaces. So we'll be talking about these general projections in this section. Okay. All right. I will begin from the easier one, the one-dimensional projection. For any two vectors, we have defined the angle between these two vectors by this equation, this formula, taking the inner product of these two vectors and divided by the lengths of these vectors. So this is our definition of the angle. Now, first, we want to find a projection formula onto one-dimensional subspace. Choose any two random vectors in n-dimensional space, and also I require that this vector to be non-zero. And I want to find a projection. Which I will denote PA of B of A. Of B onto A. Well, precisely speaking, so I want to find a projection of this guy onto the span of A. So how to find such a projection? Again, I will try to explain by drawing a picture. This is B, and this is, let me say, this is A. This is A, and this is B. So to find the projection, I draw the foot from the end point of B all the way to the one-dimensional space generated by vector A. And so that I get a right angle right here. Okay. And I believe this vector is the vector that I am looking for. Okay, this is PAB. Clearly, this vector has to be, by its definition, has to be parallel to the vector A. So that means this guy can be written as a scalar multiple of the vector A. So which I will denote by x hat times A. A is a vector, but X hat is just a number. Okay. So P A B is parallel to vector A. So let P A of B, I will write X hat times A. Okay. Now, how to find this number? How do I find this X hat? The condition here is that this is the right angle. Okay. So that means this vector must be perpendicular to A. So how do I write this vector? I guess this vector must be B minus P A of B. I should be say so. It is okay to say that vector as B minus PA of B. Okay. This is PA of B, and so this is in other words, this is just a component of the vector B. So and B minus PA of B. In other words, I am just subtracting the A component of B from your original vector B. So therefore, what remains here is just all the other members which is perpendicular to vector A. So So B minus PA. Oh, instead of writing the PA, I'll just X hat of A is perpendicular to A. That is A transpose B minus X hat A must be 0. So in other words, X hat times A transpose A is A transpose B. So X hat is just A transpose B, everything divided by A transpose and A. Okay. All right. So this is where I just ended up with very nice looking formula. So this is not well. So if you multiply this number to your original vector A, then that is going to be the projection. Okay. I have a non-zero vector A. The projection map onto A, which I will denote. The domain of this map is the entire space Rn, and the codomain of this space is just span of A. And this is defined by PA of B is A transpose B by A transpose A times A. So this is the formula. You should better memorize this, at least by the end of the semester. Okay. Just one more thing to add. So this map is linear. Clearly, this is a linear map, right? Because this map was defined by using inner product, and inner product was linear. So this is clearly a linear map. I have a application of this formula, which is the Schwarz inequality. For any vectors A and B. So what is the Schwarz inequality? The inner product, the absolute value of the inner product is always less than the product of the length of A times the length of B. So this is the Schwarz inequality. I think I mentioned this inequality just once in my previous lecture, but I have never proved this. So I guess this is the right time to do this. I want to consider the subtracted B minus A component of, so B, A component of B squared. Oh, well, this is some vector. This is a vector and vector squared. So therefore, this number is always greater than or equal to 0. But A transpose B minus A transpose A, everything times A. Okay. So I should be computing this inner product. This is B squared minus 2 times A transpose B over A transpose A times A transpose B. Okay, and plus A transpose B over A transpose A and everything squared and A squared. So okay, and now what? So I have 2 A transpose B. So I just want to square this. And this one squared, and one factor of this they cancel out. So this is what I have. And B squared minus and A transpose of B squared minus over A squared. Okay. Yeah, I think I'm done because so this number is always greater than or equal to 0. So if you solve this for A transpose of B, then A transpose of B, everything squared is less than equals to A squared times B squared. So the proof is done. And, no, so I'm not quite done yet. Why? Because, and when do I have equality? In order to have this equality, I have this equality if and only if I have this equality. So if and only if this vector equals to 0. And when this vector equals to 0, this vector equals to 0 precisely when A is parallel to B. Okay, so if those two guys are parallel to each other, then projection and B they must be the same thing. Therefore, this entire guy vanishes. So the if and only if A is parallel to B. Okay, All right. So okay. So much for the theory, and we'll go to some explicit examples of this. A, B. I have vector A, which is 1, 1, 1. B is 1, 2, 3. And I want to project this guy onto the subspace generated by this guy. Then is A transpose of B, A transpose A, hold on, okay, times A. So A transpose B, which is 1, 2, 3, 1 plus 2 plus 3, which is 6. And A transpose A is 3. So this is 2 times 1, 1, 1. All right, easy. Okay, not a big deal. Now we want to discuss the matrix representation of the linear the projection. So I told you the projection was a linear map. So a priori, so the domain of the projection map is Rn itself, and the codomain of this guy is again Rn. So if you consider the matrix representation of this map, then you're gonna get n by n matrix, right? On top of that, I wanna find a matrix representation of PA in terms of the standard unit vectors. So here, 1, 1, 1 actually represent the. So this number 1, 1, 1 was written in terms of the standard unit vectors. 1 times E1 plus 1 times E2 plus 1 times E3. So what is such a matrix representation? We write this is A transpose A. So A transpose of B, A transpose A, and everything by A. Yeah, so A transpose A, so I'll just replace it by 1 over A squared, and A transpose B A. Okay. This is the original expression, but I can just change the order. How about this? So A transpose B which is merely a number, scalar number. So maybe I can let it go all the way to the back, just like this. And also matrix multiplication is again associative. So A, T, everything times B. Okay. Now what? Here, I am considering A as a n by 1 column vector. And therefore, A transpose is n by 1 column times 1 by n row. So if you multiply these two guys, then what do you have here? Which is just n by n matrix, right? So I can say the matrix representation of this this projection map can be written as A squared times A transpose. Now, can you guess the rank of this matrix? Clearly, rank of this matrix is 1. Do you remember? So if any matrix can be written has such a decomposition, then this guy must have the rank 1. Okay. Let me check if this is true or not. If this is my matrix A, then its matrix representation must be 1/3 times 1, 1, 1, 1, 1, 1. So 1/3 times everything is the 3 by 3 matrix, and everything equals to 1. Okay. And so what was my vector? Was it 1, 2, 3? Yeah, 1, 2, 3. If I plug in 1, 2, 3, then which is just 1, 2, 3. And this is what? 1 plus 2 plus 3 is, so which is the 2, 2, 2. Okay, all right, so I'm good. Okay, so this is the matrix representation of the projection map, which is a rank 1 matrix. Okay, next. So we denote so I would say the P is a matrix representation of the projection map. Then I have very interesting 2 properties. First, P is a symmetric matrix. Okay, so it looks like this guy is the symmetric matrix. Yeah, so about this diagonal entries, so everything is symmetric. So, this is clearly symmetric, but this is not coincidence because if you take the transpose of P, then which is just taking transpose of A transpose. So this is number. So transpose the transpose has no effect. And AT T and AT. So clearly this is P. So P is symmetric. And number 2, P square is P. Again, if you multiply this matrix twice, then which is just A to the 4th and A, AT, A, AT. But since matrix multiplication is associative, so A transpose A, which is A squared, so this is again A squared A transpose. Okay, so P squared is P. But the second condition is somehow very obvious, at least to me, because if you apply two same projections twice, then that is effectively the same as the taking just one single projection. Okay. So lastly, so I want to go back to our the two-dimensional projection. So I guess you remember, so we discussed about the matrix representation of the two-dimensional projection, which was this. Okay. But this one can be understood just like this. Well, this data line, we consider this guy has been spanned by this single vector of length 1. Okay. Therefore, also, if we try to write a matrix representation of this projection map, then which is a square 1 over a squared times a transpose, but this is 1, so we can simply just ignore it. And a transpose is this, and if you just try to expand this, then FOIL out this, then you get this matrix, which is precisely as before. Okay. All right. Okay. So in this section, we want to discuss even more general projections. So so far, we have been discussing projection of a vector onto one-dimensional subspace. But there is no reason that we have to stick to the one-dimensional subspace. Maybe we can consider projection of a vector onto two-dimensional subspace or three-dimensional subspace and whatsoever. Okay. So how do you so let me discuss this n-dimensional, this generalized projection. And the best point to start our discussion is again to solving the system of linear equation, especially over-determined system. And so what was an over-determined system? An over-determined system was a system of linear equations such that number of unknowns is less than equals to number of equations. Okay, so that was the over-determined system. So generally speaking, the under-determined system may have solution, but number of solution was not the solution but the solution was not unique. But on the contrary, the over-determined system sometimes it doesn't have any solution. Okay, because you have too many equations. I have a m by n matrix. And we have, when this system has a solution, if and only if B was a element, so B was a member of the column space, right? So that was easy. So now today, I want to consider the case when B is not a member of the column space. In that case, the simple but the most concise answer is there is no solution, and end of story. So that's it. But sometimes we need to try even more. So we can still struggle to find some sort of not precise solution, but some sort of pseudo solution of the system. Something like this. I have two unknowns and three equations. Clearly, this is an overdetermined system. And well, if you spend enough time and effort solving this equation, then you will realize that there is no solution. So it has no solution just because this guy is not a member of the column space. Okay, so so over determined system. And over determined system happens when M is so when M is greater than or equals to N. So for the rest of this discussion, we will consider the M is always greater than or equals to N. Now, if B is not a vector B does not belong to the column space, then there is no solution. But what we can still try to find some X satisfying the error. So error condition. So but we can still try to find an approximated solution. So there is no solution. So technically there is no solution, but however, we can still try to find an X that satisfies this number. So what is this number? This is a difference between AX and B. If this guy has a solution, then the minimum of this number should be 0. So which is good. But however, since in this case, if B is not in the column space, then there is no such X that satisfies this guy equals to 0. Okay. So however, we know even if this guy cannot be 0, but we can still try to find an X which minimizes this number. So since this number means the difference between the precise solution and the approximated solution. So we say this is squared error, or sometimes we say this is this number as error squared. So in other words, we want to find X which minimizes the error. How can you find such an X? We say such an X is the least square solution and write X hat. This is in Rn. So we want to find X hat that minimizes the square error. Now, how do I find such an X hat? The idea is how to find X hat. We want to consider B minus AX. So B is a member of Rm, and A times X is again the member of Rm. I'm gonna draw a cartoonish picture that explains the situation. I guess, but it will help. So this entire three-dimensional space is R3, and this is the origin, and this plane let me say this plane is representing stands for the column space of A. And my B was not in column space. So I'm going to say this is my B. Okay. Now I want to minimize this vector. I want to minimize the length of this vector, right? And for any choice of x, A times x is automatically the member of the column space. So like this. Okay. A times x is here. So this green arrow represents B minus AX. Okay, right? Now, I want to minimize the length of this vector. When do you think that this length of this guy minimizes? There's only one option. So starting from this point, you draw the foot all the way to the column space. And once you have the right angle, then I guess if this is, well, for this vector, then this length must be minimized. Okay. So in other words, if when my AX is pointing exactly at this point, then B minus AX is now being minimized. Okay. Oh, great. So I'm going to say this is, sorry. Yeah, this is my AX hat. My AX hat must be exactly at this point. So, okay. So if X minimizes B minus AX, square, then B minus AX. So it must be orthogonal to the column space. But you know, the orthogonal complement of the column space is the left null space. Okay. So in other words, B minus AX must be a vector in the left null space. And being a member of the left null space means sorry, I have to put the hat here. Means this guy transpose times A is the zero vector. So in other words, A transpose B minus A X hat is zero vector. And in other words, A transpose A X hat is A transpose of B. Okay. So just take a look at this last equation. AT A X hat is AT of B. So how do I get this equation? So, well, even if the discussion was somehow lengthy, but the point was very simple. Suppose that you have a overdetermined system, and you want to suppose that you want to find the least square solution of this system. Then what you're supposed to do is very simple. Just try to multiply the transpose of this matrix to the left side of this equation. Then this equation is called the normal equation, and this what was the dimension of this guy? This was n by n, and n by n has been multiplied by n by n matrix. So this is A transpose A is just simply the square matrix, right? So this is not A over determined system anymore. This is just a regular n unknowns and n equation system. And if you can find the solution of this normal equation, then that is going to be your least square solution. Okay, agreed? Now, to make our life easier and simple, so let me assume that A is a full-rank matrix. So A is an n by n matrix and full-rank matrix. And since the number of rows is greater than or equals to the number of columns, therefore rank of A must be n, right? Being full-rank matrix means the rank of A was n. And A transpose A, well, because of our quiz or our discussion, even though I have not given you official proof of this, but if this guy has the rank n, then ATA must have the rank n too. Okay. Then what is the dimension of this guy? This was n by n. N by n has rank n. So in other words, this is a non-singular invertible matrix. Okay. Now this is invertible. Therefore, if we multiply the inverse of this matrix to the both sides of this normal equation, then we can say the least square solution is just simply this one. Okay. This one, I want you to memorize this by the end of the midterm exam. Now, lastly, so we have been talking about the projection. So now we know how to find the least square solution. Now let me go to the projection. From this picture, we can say the projection of vector B onto the column space is precisely A times X hat. Okay, X is just a least square solution, but A times the least square solution should gonna be the projection of this guy onto this space. Okay. So this last part is the theorem, but at the same time definition. The projection of B Rm onto the column space of an m by n matrix is which is A times X hat, which is A times ATA inverse times A transpose B. Okay. All right. So just one more detail. Sorry, I know I just ran out of time, but well, if your matrix is not full-rank matrix, then taking inverse of this guy is impossible. Right? So this equation, this formula or this theorem or this whatever definition is true if and only if your matrix is a full-rank matrix. Okay. All right. So thank you for your patience and see you next time. 그쵸, 그쵸. 예, 이게 풀랭크가 아니면은 얘가 인버스가 있을 수가 없잖아요. 그치? 풀랭크가 아닐 때 인버스를 구하는 거는 이제 제 학기 말에 싱귤러 밸류 디컴포지션 할 때 나옵니다.